Hello, I am presenting our work Tunable Soft Equivariance with Guarantees. This is a joint work with Purdue University and DSO National Lab. First, let us say what is equivariance. A function f is equivariant with respect to a group G if transforming the input with a group element G corresponds to the same transformation on the output. Now let's see an example of shift equivariance. Let's say I have an image of a cat and I have a model F that predicts the segmentation mask of this particular image. Now if I shift that image down, then the corresponding segmentation masks should also shift. And if our model respects this particular constraint, then we call our model shift equivariant. Many work have studied exact equivariance. That means they develop the model that respects the exact group equivariance. However, in practice, such exact equivariance rarely holds. For example, in case of shift, new background objects enter into the image, breaking the actual group operation. Same thing happens when we shift an image and the object clips on the boundary. This issue has led us thinking, how can we design deep neural networks that are soft equivariant, that means respects the equivariant loosely with some form of guarantee. Now let us define what is soft equivariance. The equivariance error is given by the deviation from the expected equivariance behavior. Now we call a model soft equivariant if this error is within some bound after normalization. Here we normalize the equivariance error with the natural local scaling of the model defined by the Jacobian. Now to understand our technique, let's try a very simple example. Here we will consider 1D signal and we will try to make a linear model circular soft invariant. So here the data is just a 1D signal and the transformation is defined by this matrix S, which is a circular shift matrix, and the constraint will be invariance. So if you transform the input with the circular shift, the output of the model does not change. And here we'll consider a linear layer. So our function f is just a linear transformation by the weight matrix, by the weight W. Now let's analyze the invariance error. The invariance error can be written in this form. Here we introduce a new notation D, which is shift matrix minus the identity. So if we take the SVD of this particular matrix T, we'll know that the U and V corresponds to the DFT matrix, and the sigma, the diagonal of the sigma actually corresponds to the different frequencies. And we can reorganize this particular invariance error as this. So we'll see that this has a direct relationship with the different coefficients of the input and the weight, and every corresponding product is scaled by the singular value of this particular SVD decompositions. And what we can do, we can bound this error term depending on this, how far or how many of this SVD we allow into the weight. Now let us enforce the band limited assumption. So if we assume that the weight matrix does not have any component corresponding to the singular vector whose singular value is greater than b, then what we can do is that we can show that the error is bounded by some constant times the cutoff value. So this gives us a control over how much the linear layer can deviate from the perfect circular shift invariance. Now let us see the visualization of what we just proved. Here we have plotted the invariance error with the increasing number of singular basis vector. And then here we are showing on the right, we are showing the visualization of the weight as we introduce more and more singular basis. We can see when the weight is constant, that means like we just have one basis, we have exact equivariance, and that is the ground truth solution to have a circular shift invariant layer. And we can also see the invariance error actually depends on the cutoff index or the number of singular bases you introduce into the weight. And that means we can control this error by controlling the number of singular bases. That means like by controlling the cutoff value B. Now, how to go beyond shift? So for any discrete group, what we can do is that we can replace our transformation matrix S with the respective group action, and the same procedure can be followed to design invariant layer with respect to this particular group of our choice. For example, it can be 2D rotation or reflection. In case of continuous group, for example, 3D rotations, SO3, we need to consider and replace the S with the respective Lie algebra of the particular group. And this method can be generalized to different types of linear layers. It can be convolution, or it can also be multi-layered perceptron. Also, it can also handle a bias-like component, just as a positional embeddings used in the transformers. Now let us see what is the process of designing such soft equivariant layer. First, we have a group of our choice G, and we have a Lie algebra of this particular group. What we need to do, we need to do a singular value decomposition of this Lie algebra, and we'll sort the bases from low to high based on their singular values. Then we will design a projection operator that filters out any singular value component greater than our cutoff value B, and we'll just plug in this filter inside the layer, and we'll apply this filter on the weight just before it acts on the input X. Now, to make the equivariant layer, we can follow roughly the same procedure. For equivariant layer, the weight will be a 2D matrix. The first thing we need to do is we need to update the group representation S with this tensor product representation. And the second thing we need to do, we need to vectorize our 2D weight into 1D. So this flattening the weight matrix, and we just follow the same procedure, and we'll get our soft equivariant filters. However, one problem is this matrix, this tensor product representation, can be quite large, and it might create a bottleneck while doing the SVD of larger representation. So in the paper, we propose a very fast technique to construct such filter using Schur decomposition, which brings down the time complexity from d power 6 to d power 3, where d is the dimension of the representation of the group. Now we will see the action of our soft equivariant filter on a pretrained model. Here we chose VIT's patch embedding weights for visualization, and our transformation is 90-degree rotation. Here we see for full equivariant model, there's a strict symmetry on the filters of the patch embedding layer. And for the complete non-equivariant model, that means the fully untouched pretrained VIT, there is no such symmetry inside on the patch embedding filters. And we see that while we go from the full equivariant model to non-equivariant, the symmetries gradually break. We can also see that that effect on the structured feature of a 90-degree rotated image of a cat, and we see that the error grows gradually as we go from the equivariance error grows gradually as we go from full equivariant model to non-equivariant. We show the performance of our model on ImageNet classification. We report regular accuracy. And combined accuracy, which is a combination of accuracy on the rotated data, which is rotated with an angle negative 30 degree to 30 degree, and the accuracy of the clean images. And we also report the invariance error, which is the prediction difference between a rotated image and an upright image. And we see in all the cases, our method improves the accuracy and this combined accuracy. And we also outperform the baseline canonicalizer, which is also a method to impose equivariance on the pretrained models. We also show our effectiveness on the segmentations. So similar to the classification case, we report MIOU and combined IOU, which is the combination of IOU of the augmented and the clean image. And we also report equivariance error, and we see that we improve the performance of the pretrained models. So the final takeaway is we are presenting a technique of constructing soft equivariant layer by analyzing the Lie algebra of the group and taking their singular value decomposition as Schur decomposition. And this method can be applied to any pretrained vision models. Thank you.